All right, welcome everybody. We have Ash here for his talk, Composing Magic.
Yeah.
Go ahead, Ash. Do some explaining real quick.
Yeah, really quick. So basically, this is a pretty heavy talk. There's a lot of concepts, and I wanted to pre-record it so that I could be in the chat session doing more explaining. So between the slides, the video, and my chat that I'm going to be spewing as we go, hopefully the whole system will come together to make sense. So yeah. It should be interesting, and read up on the chats, and definitely at the end I'll come back and answer any questions. But hopefully it all makes sense.
Awesome. All right, we will get started. Remember, down in the bottom corner is the Slack channel to use to ask your questions. And with that, we will get it started.
Thank you, everyone, for coming to this session, Composing Magic. I want to share with you all the resources that go along with this talk. To find the resources for this talk, simply go to the conference website and then look at the description for this talk. You're going to find a link to the slides and also a link to the GitHub repo for the code that we're going to be reviewing. When you go to the repo, make sure that you're looking at the 360 AnDev branch. If you'd like to know more about me, you can just look up @biocodes. I'll take a second to review the application that goes with this talk. This application is made out of two composables. One composable shows a list of words. The second one allows you to add new words. So here we can make a retrofit API call out, which will add to our list of words, or we can go and use this text field to add a new word. This application is being driven by the MVI architecture, so our view has three states that it's paying attention to. One is a list of words. Two is if the system is being able to be edited or not. And if we go into a state where we can't edit, the compose re-renders itself completely. So here we can see the list text field changes. This plus goes to an X. And when we go over to add words, you can see that both buttons are disabled. What's interesting here is, as we enable and disable the editing, the constraints are actually moving the buttons up and down. And since we're using the constraints to move the buttons up and down, this is probably a way that we could do motion layout with the constraint system. Now, if I go ahead and add a word here, you notice that we go back to the main window. We can also delete all of our words. This navigation is being done by just swapping out the two composables. So here you can see this text field does not change as we go from one composable to the other, because this is a column of two composables, where the top one is just a text field and the second one is the composable that's being flipped out. And this kind of goes back to how currently we do navigation, where we have a main activity and we're changing the fragments as we navigate. And for completeness, we have a way to get a network image by using coil. So coil is being used to show a network image. I just wanted to take a minute to review what this talk will cover. On the right-hand side, you're going to see the file system for the repo. On the left-hand side, you're going to see the Android architectural components that we're using. And now I'm going to make a one-to-one mapping between the components and where the source code is. So the UI is built by composables. In the UI directory, you're going to find the main composable, and this is where we hold the list of words. When we want to add a word, that's in the add word composable. We're using an MVI architecture, so under model, you're going to see MV actions. That's how the composable sends messages to the view model. And then the channel is actually in the view state. We're using Kotlin Flow instead of Livedata, and that's coming out of the Room database. And we're using coroutines for all of our threading. And we're making a retrofit call out from the remote source, and the API is under the example API here. The application starts with the main activity bringing up the main composable, but we're actually using Dagger Hilt, so we have to have this app that brings up all of our dependencies. Our dependencies are all held in the DI directory, and we're using the MVI design pattern, and we're going to get deeper into what MVI is next. When we start learning about MVI, model view intent, reading different blog posts, we see that they're usually talking about RxJava. RxJava is a reactive framework, and it lends itself very naturally to MVI design pattern. The MVI design pattern is unidirectional cyclic flow. What happens is the user, it produces some input. That input updates a model, and that model generates an output, and then we continue on this cycle. The problem is that even knowing MVI is a beautiful design pattern, RxJava has such a high learning curve that it really keeps us from wanting to use the MVI design pattern. And if we look at a typical post explaining how MVI works, we can see in these 8 parts that every part is really focused on using RxJava to get that piece working. To help us understand how MVI works, let's first start with how MVVM works, which is the current way the Android architectural components are put together. So we have a view, and that view generates intents, and those intents update the view model, the state, the repo, the logic. And once the view model is updated, the data is bound to the view, so it updates the view. So in MVVM, we have the view sending intents to the view model, and the view model rendering the view. Now you might look at this and say, this is unidirectional cyclic, so why is this not MVI? And we're going to get into that in a second. One of the very first examples I've seen of MVI was this post. And the beautiful thing about this post is that it doesn't use RxJava, and it's the absolute most minimalistic MVI example I could find. So at the end of this talk, if you're still kind of confused and you want to see a very, very minimal example of MVI, this is the post I would refer you to. Diagram to explain how MVI works. It has 3 phases it goes through. It goes through a listening phase, a business logic phase, and a rendering phase. And again, it's cyclic and unidirectional. So what happens is the user interacts with the UI. This generates intents. These intents go through an accumulator where we figure out which intents we want to deal with. If there's not that many intents coming into our system, we can just go ahead and go into the reducer. What the reducer does is it looks at the previous immutable state of the application. It takes that previous immutable state and it adds it to the changes that are coming through the intents, and it generates a brand new immutable state. And it's really important that it's an immutable state, because at any time that we want to do debugging of our system, we can simply look at the state that it's currently in. There's only one and it's immutable. So it's really easy to reason about what our system is doing currently. So now that the reducer has generated a new state for us, our database is updated, and the view model then goes ahead and sends that through the renderer to the view. And the view knows how to read the new view state and update all of its views. And so this is basically the key pieces of the MVI architecture, that we will be generating a certain number of intents, and we can just reason about our system very easily because we have a Kotlin sealed class that tells us what all of our possible events are. We're speaking on this channel, and through this channel, we're talking to the reducer, and the reducer is taking our previous state and generating a new immutable state for us. So this is very, very much like MVI, but we're adding these intents in the channel, and we're adding a reducer, and we're adding an immutable state that is being used by our view to render the new view. Now that we've seen a diagram of how MVI works, let's go ahead and look at the source code to make it more concrete. So we just want to go to the GitHub repo, make sure we're on the 360 AnDev branch, look inside app, source, main, application, model. So the VM action is how the UI communicates with the view model. These are all of the messages that the UI can send to the view model. We can either change the editing or update our list of words. Since this is a sealed class, if we make any logic mistakes, the compiler will catch it for us. And the way that the UI communicates with the view model is through this channel. And we're going to talk about hot channels and cold flows in a minute in this talk. So basically what happens is when the UI wants to send a message, it offers the intent on this channel. If we go up to the model, go to the view state, this is the current state of our application. Progress and error have not been implemented yet, but our app state can either be editing or not editing. Again, it's a sealed class. Our list of words are coming up from our repository. So anytime we send an intent that needs to update the words, we go to the repository and we get those words and we update our view state. Now, this is all of the messages that the UI can send to the view model, and they're actually coming across on this channel. This channel is a hot channel for the composables to communicate to the view model. The way the view model communicates with the UI is through this mutable state flow. This mutable state flow, it's a cold flow that has the current state of our application. And we make this a val, so it's immutable. We give access to the UI through this getter, right? So this get can only read our view state. It can't change it. Again, it looks like it's immutable. Now, when the UI sends a message on the channel, we don't want to just read the channel. What we want to do is we want to consume it as a flow. So we get those intents. And remember, we talked about a reducer. The reducer takes those intents and figures out what needs to change in the current view, state. So it takes those intents, it copies the current view state, updates what needs to be updated, and emits a brand new view state. That view state is then put into this immutable state. And since this is a reactive stream, it's a flow, the UIs will see that change and they know how to re-render themselves by observing this flow. I wanted to point out another blog post that I think is of much use to us. This blog post is very similar to this talk, except instead of using composables, they're using the standard XML, and instead of using Kotlin Flow, they're using Livedata. So if this talk is adding too many new components, you can always drop back to this posting, which is probably a little bit more familiar. So we're going to get deeper into what channels and flows are in a minute, but I wanted to give credit to QuickBird Studios for this post, because this post was the first time I saw someone use mutable state flow in the MVI pattern. And the article is interesting because they start out with 2 channels. But when you use a channel, you have to manage the resources. But if you use a flow, the flow starts when you first connect to it, and it's cleaned up when you disconnect from it. So you don't have to manage any of the resources. And using a mutable state flow is perfect because the state it holds is confluent. So when the reducer is done making the brand new immutable state and it pops it into the mutable state flow, the other one is completely deleted. And the UI gets access to the state through this reactive stream. So once we update that state inside that reactive flow, the UI is notified and it knows how to re-render itself. And this state is perfect to represent any type of state in your system. Kotlin channels are a way for 2 coroutines to communicate. A long time ago, when we did threading code, we used to have threads communicate by having shared memory, and then we have semaphore locks and different locking methods to make sure that we don't corrupt that memory. But Kotlin channels flips that, and instead of trying to share memory, they do that by sharing communications. Touched on what a Kotlin channel is. Why do we say that Kotlin channels are hot streams and Kotlin Flow, which is an asynchronous series of events, a cold stream? Well, a hot stream or a cold stream can be defined by 3 properties. 1, where's the data? 2, how many receivers? And 3, when does it start and when does it stop? A channel, which is considered a hot stream, we say the data is outside the channel, so that whenever anyone communicates with that channel, they're all looking at the same data because it's not inside the channel. You can have multiple listeners listening in on the same channel, and the channel exists even if there's no one that is connected to it currently. So it exists before there's any receivers, and it exists after all the receivers are gone. How does that compare to a flow? A flow is considered a cold stream because the data is inside the stream. It's also a one-to-one. So every single time there's a receiver, it starts up another stream. And two, it does not exist until there is someone to listen to that data stream. So before someone uses that data stream and after they're done, that data stream does not exist. Now, one of the really nice ways I've heard about explaining the difference between a cold and a hot stream is by using the radio and CD analogies. So a radio is like a hot stream. It has multiple listeners listening to the one channel. The streams exist even if there's no one listening to them. And the data is coming from the radio station, so it's not inside the stream. Whereas CD is considered a cold stream because every single user has their own copy of the CD. The CD, you're not going to be listening to it until someone puts it into the CD player and starts playing it. And the data is inside the CD. So when you talk about initializing a hot stream, what you're doing is you're getting live data off the air. When you talk about initializing a CD, you're getting the first bit from the first song every single time you start that CD. The creator of Kotlin flows and Kotlin channels doesn't think of it in those terms. He thinks of it in terms of synchronization, where Kotlin Flow does not require any synchronization because it's just an asynchronous data stream. Channels are wonderful for synchronization. They're hot and they're good for network connections and events that are being streamed. One thing to really note is that channels are not scoped to a specific lifecycle like a flow. A channel survives across screens and lifecycles. Okay, so now that we've gone through channels and flows, let's go back to the view model and walk through the code. Here, we see that we have the user intent channel. So this is a hot channel. It exists no matter if there's subscribers to it or not. And on this channel, the UI is sending the user intents. This is a channel that we need to manage. We have a mutable state flow. So this is a reactive stream. It's cold. That means that the resources are going to be managed for us. When the UI connects to it, the flow will start. And when the UI disconnects from it, the UI will be cleaned up for us. Now, unlike a normal flow, this flow has a state in it that is not the initial state that the flow starts with. It's the current state of our system. So you can kind of say this is kind of like a hot channel and kind of like a cold flow. So we'll call it a warm stream. When the UI wants to send information on the channel, we're actually going to consume it as a flow because we really don't want to just sit there and listen on the channel. We want to consume this as a flow, and we're going to collect those intents. And so for every intent that comes over, we can collect that one intent, and we can read that intent. We give that intent to the reducer, and then the reducer updates the state inside of our mutable state flow. And since this is confluent, it's going to destroy the previous view state and put a new view state in there. This is a reactive stream. So what happens is our UI gets notification that there's a new state. And it's going to go ahead and collect that as a state. And at that point, it's going to use that state, and it knows how to re-render itself dependent on what is the information in that state. Now that we've seen StateFlow, it's interesting to point out that the Kotlin team is moving forward with more cold flows that have properties of a hot stream. So they are currently in discussions about how to build a shared flow. And a shared flow, we can see, is going to be used for advanced state sharing. So it's a flow implementation that is hot and shares image values among all the collectors. Now, it's kind of interesting. We have StateFlow and we have SharedFlow. I wonder in the future if we're going to have MVI flow. So as all of these different flows are being created by the Kotlin team, we could see maybe new paradigms coming up that are even going to be more beneficial to us when we try to build an MVI architecture. Reviewed the MVI design pattern. Let's see how that fits into all of the new Android architectural components that are coming down the pipeline, like Compose, Kotlin Flow, and coroutines. I have to say I'm really excited about composables. If we look inside main Compose UI, we'll see that we can build an entire recycler view with one line of code. And here we can see the view is reading on the channel the current app state. And depending on if it's editable or not, the component dynamically updates. Just as a side note, I want to say how interesting it is to watch Jetpack Compose evolve. In the beginning, their modifiers were very, very different than the way SwiftUI did it, and now their modifiers are very similar to the way SwiftUI does it. At how composables do constraints, it's very interesting. So inside add word compose UI, we have two constraint systems. Constraint on the text field and a constraint on the buttons. And depending on the state of the app, the buttons are either on top or on the bottom of the text field. And we can see where this would lead to motion layout. Navigation for composables is still a work in progress. If we look inside main activity, what we'll see is they're using the state of a screen to know which composable to show. This is very similar to how navigation works today, where you have a main activity and you're flipping out different fragments as you navigate. One of the other very interesting points about Compose is that what you do is you lift your data to the highest common denominator, composable, and then pass it down so you have a single source of truth. And you do the same thing for the functions that you're putting on your buttons. So you're passing them down through the composables the same way you do your data. We are now able to use Kotlin Flow instead of Livedata because the Android architectural team supports Flow right from a data access object. So no longer do we have to bring in all the live data libraries. The language itself supports Flow, and Flow, being an asynchronous stream of events, is actually doing the same thing that Livedata is doing, and we can remove our libraries for Livedata and just rely on Kotlin Flow. If we look inside the state model KT, we'll see Dagger Hilt dependency injection. Two things I really didn't like about Dagger was all of the scoping we had to work out, and all the boilerplate. And that's one of the reasons I really like Dagger Hilt. The scoping is just done with the add install in annotation, and it removes a lot of the boilerplate for us. Just for completeness, if you look at the bottom of main Compose UI, you'll see an example of how to use coil inside a Compose. I've seen examples of Glide and Picasa, but I haven't seen someone who did coil in a composable. So I just added this one little example. So this brings me to my final thought. And it's interesting if you look at the work that the Kotlin team is doing. They know how to take things that are fairly complex and make them very easy. So they took something that was really complex like threading and made it almost as easy as writing synchronous code. And so as I move forward, I'm pulling out all my RxJava threading code and using coroutines, because I was just using RxJava for threading when it was really meant for reactive streams. And now we have Kotlin Flow for our reactive streams, so I can go ahead and remove RxJava completely. So I go from a very complex RxJava environment to a very simple Kotlin environment. And if I look forward, I'm just wondering, I have my StateFlow, my SharedFlow, and what other flows are the Kotlin teams going to work on? And how is this going to enable my code going forward to be simpler, and I can reason about things a lot better? That coupled with what the Android team is doing. And if the Android team is building better architectures for us, and the Kotlin team is building better language constructs for us, there might be a time in the future where Kotlin supports MVI and the Android development team decides to embrace MVI so that we will move from an MVVM architecture that we're currently on to an MVI architecture. And that's why it's important for us to learn MVI now, so that if the Android team does make the switch to supporting MVI out of the box, we're ready to start using that pattern. I really wanted to cover how SwiftUI and the combined framework compare to Jetpack Compose and Kotlin Flow with SharedFlow, shared state, but I just absolutely ran out of time. The good news is, in August, there's the 360 AnDev conference that's put on by the same people who put on this conference. And there, in a Sunday session, I will be doing an entire day tutorial on SwiftUI and the combined framework. And I will touch on how it compares and contrasts to Jetpack Compose with Kotlin Flow. I want to thank everyone for coming to this talk. It was pre-recorded so that I could focus on all of your questions. Hopefully I was able to answer all those questions. Again, thanks a lot for coming, and if you're wondering what I'm up to, you can always see where I'm talking at or what I'm doing at BioCodes. Thanks, you guys.
Awesome, thank you. That was amazing. The Q&A section was fast and furious. Ash, any final kind of closing remarks?
Yeah, I just had one question about, is there a warm stream that's a single instance that shares only broadcasts when it notices a listener is attached? That would be the StateFlow. So if you look at how the StateFlow works, basically it's a warm stream that is reacting when the state changes, and then the composables just react to that. So it's a really nice architecture. We don't have to worry about managing anything. The whole thing is managed for us by the infrastructure.
Nice.
Yeah, thanks.
Perfect. All right. Well, thank you, Ash. We will see everyone back here in about 4 minutes.
Thanks. Thanks, everyone.